Hello, everyone. Welcome to Fresh Concrete. I'm delighted to welcome you to the second of this year's Fresh Concrete events. It's produced in collaboration between the Concrete Centre and the Building Centre. My name's Elaine Toogood. I'm Director of Architecture and Sustainable Design at the Concrete Centre, and I'm going to be hosting today. So this series, if you're not aware of it, has been created just to showcase just some of that really wide-ranging innovative practices, new types of concretes that are emerging, a lot of them to address climate change, either through mitigation, adaptation, or both. So they're basically technologies that bring a fresh approach and fresh thinking to the way that we make and use concrete. And today's talk is no exception. It's focused on an innovative vascular delivery system that's embedded in concrete to release self-healing agents into that concrete element. So in a moment, I'm going to be introducing you to our speaker, Dr. Sijing Li. She's going to join us. But before we do, I'm going to provide a little bit of context to this system, which is using self-healing concrete. But it is a newly patented system, and it's currently being trialed for use in rail infrastructure. So I'm really looking forward to hear what Liz is going to be saying to us in a moment. Oh, let me just go back there. So first of all, I just want to introduce, of course, one of the benefits of concrete is its robustness and durability. It needs very little repair and maintenance, certainly by comparison to lots of other contemporary structural materials. And as a result, it is widely used in infrastructure, often also in the harshest of environments, whether that's below ground, on the coast, in the sea, often in places where access for repair is limited, but also where design life needs to be long and really benefits from being long, expecting to exceed 100 years. But that's not to say concrete is completely maintenance-free, especially in such challenging conditions and over such a long period of time. And of course, with an increased focus on circular economy, the benefits of looking after the health of our infrastructure and buildings is even more important, and also to support longer life. That's a key way of doing that. And of course, what that does as well is reduces the associated carbon expenditure associated with repair. Now, self-healing concrete is a new technology that can assist with that. You might have come across it before in the form of using bacteria to create calcium carbonate. This is also sometimes called microbially induced calcite precipitation, or MICP. In fact, in our Fresh Concrete 2022 series, Vinesh Das of VP Concrete gave a presentation about its use, specifically there for use in flood defences. And in our current edition of Concrete Quarterly, we actually feature some more innovation that they're taking part in with East London University. But today's event is slightly different, and it's a self-healing system for concrete that's not based on bacteria. And so with that, I am going to invite our speaker, Liz, to share her screen and switch on her camera. Now, and while she's doing that, I'll just introduce you to Liz. Excellent. So Liz is co-founder and chief operating officer for MimiCrete. Liz, I can see you.
Thank you so much, Elaine, for your kind introduction and inviting MimiCrete to have this presentation. So, as Elaine mentioning, MimiCrete, we are a startup company from University of Cambridge, working on self-healing materials to provide a more sustainable and durable environment for the build, particularly for the construction sector. So, as we know, that is this massive challenge that we're facing in the construction sector, where like the durability, sustainability challenge is happening, and then especially for the infrastructures, because if we see like the fundamental infrastructure like the bridges, tunnels, and those massive structures, when the crack appears and we have to send people, engineers, developers to fix a crack, but most of the time, after 5 years' time, we have to fix them again. And to fix this repair work over and over again is basically very costly and very ineffective. So what we're trying to do is really to make the concrete, which is the world's most used materials, and to be less destructive for our environment. Also, not mentioning the environmental burden that around 80% and even 35% of the total construction replacement activities is related on that. So, um, for MimiCrete solution, we're really trying to provide the durability, sustainability function for the concrete material, where we get inspiration from the nature, where we see the human mammals or even plants. There are a lot of vessels, veins actually happening on in our body, and when the crack appears, actually these are actually triggering the self-healing process for like a natural world. So why can't we use similar concepts to make our concrete, the buildings, be more durable, like a living creature? So in that case, we are embedding a vascular self-healing system to concrete. So imagine that concrete also has veins, and these veins are able to heal the crack in the same way that our human body works. So if you can also see one of our like a prototype that we show in on site is basically that where the crack appears and then is automatically healed by the heating agent or like by the blood. So how exactly it works? We make it like a very simple schematic diagram to show how exactly it works. So what is the vascular self-healing system? So you can see from the second diagram where the green part, which is the vascular structure, we make it in a very simple shape, which is not the one that we were currently having. So it's a physical polymer-based tubing system that are clipping on the top of the reinforcement. And then if we zoom into those the vascular system, you could see it's like a two-part of system. The external part is the tubing system, and then the inside is the healing agent. So we're having the vascular MimiCrete system to deliver the healing agent across the block of the concrete, and then serving the blood in the middle of the tubing system to deliver when the crack appears. So then it will be activating ways by the catalyst or by physical triggering. So then it will be healing automatically as it is. So where are we now? So our technology is specifically targeting on repetitive loading triggering damage, and we're focusing like environmental induced damage as well. The crack size from like mid to large size of the crack, and we're protecting the reinforcement as well because we're also providing additional water impermeability for the function for avoiding water to penetrate through the cracks, but also enable multifunctional healing agent supply where we're able to have different type of agent like polymer, mineral, even bacteria. So we are currently at the technical level, readiness level of 6, where we completed commercial relevant environment trials since 2022, and now we got our patent published earlier this year, and we're progressing to TRL7, which is to validate the product on site, and which we will be explaining in detail in our railway project. So, oh, sorry, another point that I want to also emphasize. So this is one of our earlier stage prototype that we produced. You can tell this is like the tubing system are embedded on the top of the rebar. It's super easy now that we're revamping that. So the joiner just have to clip on a few clips on the top of the rebar and that's done. And this technology can be applicable to different types of applications, ranging from precast element like the retaining wall structures or like the sleepers, or to large infrastructure like the tunnels, bridges, or the reservoirs, so on. So it's very easy to be adapted, and also having a really wide range of usage for different applications. So why now? Because we know this vascular cell. We know that there's an emerging like market for self healing, especially for demanding on the durability of the sector, providing the urgent requirement for net zero goal. And also, there's around 37% of cargo rise for self healing material cells by 2027. And our technology is not happening from zero. We've been evaluating and testing the technologies over years since we were in part of the University of Cambridge project from M4L, all the way to arm for our project, and then the time 2021 where MimiCrete started funding the company. So uh, there are a lot of self-healing or self-repairing technologies are available in the market, but they're targeting on different types of healing and different types of focus. So that's why we're just doing like a quick scanning of the differences between the technologies. So the normal benchmark concrete is the one that we're using traditionally, like the one with the reinforced concrete. Normally, they have autogenous healing at the very beginning because concrete is still young, and they can react with water and then fill in the early cracks. That's possible. But after this reaction finish at a later stage of the concrete, then there's no autogenous healing afterwards. So people get inspired of trying to extend the autogenous healing by adding, for instance, the admixtures, waterproofing materials as a coating materials. There's a lot of big names using these type of technologies, targeting to heal the crack around 0.4 to 0.5. But then the same after the material being used up, there's no like follow-up healing, but there's good for like water proofing. And then for the bacteria, as we mentioned in earlier stage, that some of the bacteria can be capsulated in the capsules and then mixed together, and also targeting like from small to large cracks. But also there's a few like different focus regarding the bacteria focus. And vascular structure, we're having a specific, unique focused, really targeting on the mechanical recovery of the building, but also to be able to have more flexibility for the healing agent. Since we're trying to target to have like a solution that are able to tackling, like for instance, the water defense, which require like a very quick reaction, and to avoid water to get into concrete for the corrosion. Or there's other scenarios that requiring like a more similar concrete interaction concrete format. So then the requirement of the strong, very strong like stiffness would not exactly the same alignment with the requirement afterwards. So we're trying to focus on different type of element, different type of requirements for the sector to be able to enable more opportunities. So that's why we're summarized here on the left hand side, right hand side, that we're targeting all like crack size from like small to large. We're able to heal large cracks, even larger than 1 millimeter. And also we're able to enhance the mechanical performance even at the beginning, where we did an investigation earlier on to say that actually vascular structure itself can somehow distribute the load, acting like a semi reinforcement. That's why we're able to provide the extra mechanical performance even at the beginning. Also, by having this connective vascular structure, we're able to enable multiple healing events. So then, even when the healing agent is being used up, we can also to refill more heating agent back. And then adding up to like a low labor maintenance afterwards, and follow on for the maintenance cost as well to have a further reduction. So our technology is especially wanted to enable a much safer built environment by providing much durable and clever, intelligent materials in concrete. So and also, which is ultimately going to help us to reduce carbon emission upfront, and also for the life cycle maintenance consideration of reducing the repair and replacement activities related carbon emission. And in general, this is how we're trying to help the sustainability development goals of 9, 11, 13 to enable much sustainable, smarter, innovative, and to low carbon type of solution for the built environment. And MimiCrete is not only working by ourselves, so we're working with multiple sectors across our value chain, like we're working with construction asset owners, we're working with contractors, working with universities, we're working with standard bodies, polymer providers, cement manufacturers, and so on. And we have been having a lot of tractions and projects going on with commercial trials, such as with the project with Natural Grill, with JCRE, and also with the project in even the EU, like with Ferrovio, and with a standard body, the AMRC. So we are really trying to accelerate our technologies to be able to launch to the market, and then people can use it as soon as possible. And one of our portfolio projects is that we've been funded by GCRE and also the Department for Business and Trade. Specifically, we're deploying our technology on the developing side of the new innovative station in south part of Wales, where we successfully delivered phase one in 2023, and now we're starting to deliver the phase two project on the site, where we're already starting to design and deploy the technology on the relevant retaining structures and sleepers together with the wider group of the team. So in general, MimiCrete is aiming to, as we said, aiming to launch our product by 2026, and in the meantime, accelerating the testing procedures, validation, and then enable like certifications to be able to give us a green light to move to the market. So that's a very, very brief and in a nutshell of our route to market, and I hope this information can be helpful for the audience to maybe collaborate, maybe have an interesting conversation afterwards. Thank you so much for your attention.
Thank you very much, Liz. That was a great introduction to MimiCrete. Thank you. So if you maybe stop sharing your slides, unless you might want to refer to them afterwards, I don't know. Excellent. So we've got a few questions coming through. So thank you for that. I wonder if do you want to talk just a little bit more about the work that you've been doing with the rail industry? What stage you've been doing some testing, as I understand it? Do you want to talk a little bit more about where you've got to with that?
Yes, thank you very much, Elaine, for the question. So yes, we're working with the rail sector, which is especially is in the south part of Wales, close to Cardiff. So they're developing a 400 million pounds project to develop the UK's first innovation station that enabling multiple innovation technologies. So MimiCrete is one of their contractors to deploy self-healing technology in the relevant structure. So recently, what we're being allowed to do is basically to work on the retaining structures and also relevant with sleepers, with the track work. So now we're working with the wider team, with like, for instance, with Atkins, with the general GCRE construction team, and also with the McDonald's to work on the whole kind of project to deliver. And we are currently on we're planning a few site visits as well with GCA during the phase two. And also we have a full-on kind of data collection planning and the site validation with the team in general. So by the end of the year, we'll be able to have a full-on kind of understanding of the site performance once the data have been collected by the end of the year. And also, we're also happy to share more updated information when we finished all the validation. Thank you very much for the question.
Right. Okay. So you mentioned a site visit there. Are you saying that this is a place that other consultants and are able to come to at some point to have a look at this in action?
Exactly, yes.
Right.
And also a great news is that they're also planning to house some of the innovations to the railway museums. And also we're on the process of planning the showcase or exhibition type of format with the team. So then we will be able to show like the how it actually really works on site. So then you don't have to all the way rush to the train station. It just like looks really plain and concrete, but actually we could try to break down and then to make it transparent somehow so you can see how it actually working. But we're still in a discussion of how to make it more kind of easier to people to understand the process. So this is on a process, but we're happy to share once this has been done. So we're happy to invite more people to join us and discuss.
Fantastic. So the way that people would stay involved with that then is to do, I guess, follow your website for updates on that, or is there
Thank you so much.
I mean, we could share some details with people afterwards if there is somewhere that they can go to if they're interested.
Exactly. Thank you so much for this as well. So I will keep you posted in separate way, but also please follow us on our website or LinkedIn page, or like we're posting the informations related. But in a separate way, we're all happy to keep you updated for the group.
Yeah. So are you anticipating, so just so I'm clear, are you anticipating that it's at the end of this year then that that
That
sort of
should,
more public
yeah,
awareness and visits can
yes,
happen. So we're
yes,
looking next
yes,
year, aren't we, for that to
yes, exactly, yes,
okay, all
yes.
right, that's good to know. Just so I get it in my diary at the right.
Thank you very much for asking.
So as part of that work that you're doing, are you exploring, as part of it, looking at the cost effectiveness of the process? So we've got a question here about implementing it in terms of the benefits of material and maintenance costs, obviously. Do you think at the moment there's an opportunity there to reduce the amount of concrete cover or admixtures? So, or even maybe the reinforcement requirements? Can you talk a little bit about that sort of equation of the cost effectiveness
Yes.
of, I'm sure that's a question you get asked a lot.
Yes, this is a great question regarding the cost effectiveness. So regarding the life cycle a cost reduction theory, or what we were doing as a cost reduction analyst, which is part of our preliminary LCA. So we did like 120 years of modeling based on the data we have from the industry to really see like how much reduction we could help to the industry reduce the cost. So we did like, especially we're working on the railway sector and also relevant with the highway sector, is that normally the structure, the service life would be around 30 to 40 years as an average service life. And then our technology is aiming to double or even triple the service life that we're able to provide. So then we did 120 years of model, and then we figure out that actually once the whole life cycle has been completing, we should be able to help to reduce around 60% of the cost reduction of the life cycle, which also when you were mentioning like the maybe like new technology would potentially have a little bit added cost up front, and we only have like very low added cost up front, so which means that the later stage life cycle benefit will definitely cover the beginning part. And a lot of industry people are like the partners we're discussing, they're really happy to see it happen, and they don't think that the amount of added cost is too much for them. Their thinking is acceptable, and it's also they're looking for a long-term value that they were providing. So this is a really great question. Yes.
Yeah, okay, excellent. Oh, that's good. So we've got a few questions here to just understand a little bit more about the process. So, and I'm going to break this right down. I'm an architect, of course, so limited understanding of all of this stuff. But so we're talking about basically empty tubes at the point with which it's installed on and fixed onto the formwork. Is that right? So there's
Yes, exactly.
okay. And then at what point are they filled and what are they
I
filled with?
Yes, so in a quick wait, sorry, in a brief way of describing it is we do a comparison. If you see like a normal precast concrete, prefab concrete, and we do the same mold either by steel or by wood, and then we place the reinforcement and then pour the concrete in. Our solution we use the same mold, same reinforcement. We're not changing the standards, and then we just clip on the vascular tubing system on the top of the rebar. We fill in the concrete mixture and we wait it for casting, for curing, and then after the curing process completing, we then refill the heating agent in. So it's more like a easiness of a logistic consideration. So we can do either when it's been loaded on site and then we refill, or we can do it in the factories, depending on how you're thinking about the logistic for the transport.
Right. Okay. And can you talk a little bit about what you are filling that with then? Because I think I've noted down specialist healing agents is what you wrote down. But are you able to talk a little bit more about how that works, what that is, and how that works? I mean, I know that's your secret sauce to some extent. I think I'm not sure, but are you able to talk about that?
Yeah, so regarding the healing agent, we are pretty much divided into like widely three different categories. So for instance, I would say polymer-based, mineral-based, or bacterial-based. But bacterial-based, of course, is like they have a separate channel to actually even to turn it on. But we're just saying it's a potential to work together with bacteria. And the first two category, which are the polymer and mineral-based, is the main type of heating agent we're currently working on. So for the interaction, it's basically that when the tubing system has been either triggered by physical cracks, which the cracks will, because we have a really good bonding behavior between the tube system and also between concrete. So the crack will directly penetrate through and create the rupture of the tubing, and then release the healing agent. The healing agent will be interacting by like catalyst, either by the UV light or other catalysts we're demanding, especially like we could even add a second layer of the catalyst, or we can add like another like a trigger, for instance, like by moisture or by others. So it's very like, how do I say, it's very different depending on what we're expecting and how quick we want this to be healing. And of course, when for different materials, like they can heal very quickly in a few seconds or a few minutes or even like a few days, but it depending on like the performance you're requiring. So for instance, some of the materials, the healing agent we're adding in can react really quick, but then the stiffness can be even 150% higher than the original stress performance, which in some type of scenario we don't really require that. So we somehow like balancing to use the mineral together, which means we're trying to lower down the stiffness, but also trying to make like more similar like concrete form. So there's a totally depending on like our client's requirement, then we're tailoring the healing agent for the reaction and for the time for curing.
Okay, so it's those different types of healing agent technologies is what you're also testing
Yes, exactly. Yeah.
down in Wales. That's part
Yeah.
of that whole
Yes, exactly.
process.
Yeah.
Okay, all right. So that's interesting. So really what's very different about this is the method of delivery of how that can be put into the concrete,
Yeah.
therefore, through
Yes.
the tubes, and so that's and that opens up opportunities for different types of healing.
Exactly. We don't have a limitation.
And that's right. Okay. So I think that might answer some of the other questions that have come through, which is trying to understand about if the tubes are placed in the middle, but the cracks are on the outside, is there a maximum distance that of how far apart they are, and how do they relate to each other, and the locations of the tubes relative to the cracks? Are you able to does that make sense, that question?
That makes perfect
Yeah,
sense.
okay.
Yes. So regarding like, I think the question is mainly about concerning about if the healing agent are able to heal the crack if the distance is in a different way. So the reason why we're focusing on precast for the time being is because the loading profile is very classic. We know exactly where the crack happening. So then like we're perfectly dealing with this scenario to make sure that the healing agent, the healing process will cover all type of the cracking events across the targeted precast element. And of course, when it's come to more complex structure, like the whole, even for the on-site pouring process instead of prefab, then we have to also work together with the designers, with the architect to really figure out how much cover we have to leave for that performance. So this is the conversation, because we don't work by ourselves. And also put it in here as well to emphasize that we're not trying to go over the standard. We're fitting with the standard and make sure our design, our performance can align perfectly well with the requirement of the strength requirements. So this is what we're trying to do. And regarding within the right coverage of the heating agent, we're normally the heating process, we normally do like it's more like the mechanism of the capillary force. You might be familiar with pressure, so then it will automatically drive the heating agent to heal like to those different cracks. And sometimes the cracks are quite connected, so then it's also easier for the healing agent to deliver. So that, I hope that answers the question.
Yeah, I think so. I mean, there's still lots of work to be done, and but that's what's exciting, is that it is bringing a new potential and way of looking at this. There's a question here about the potential use with other types of concrete, so maybe LC3 or alkaline activated concrete using alkaline activated cementitious materials. I guess the question there is potentially depending on the system of self-healing, but are you testing specific alternative concretes yet, or are you looking at Portland cement based
we are currently
that you're going to be testing, I suppose?
No worries. I think that's amazing question, because it's also opened up our opportunities with new type of cement concrete mixture. So now we're working with self-compacting concrete and also with normal Portland concrete based Portland cement based concrete.
Okay.
But also we have a great potential to work with other type of technology, specifically like low carbon cement, because sometimes we hear some feedbacks, particularly from the cement manufacturer, that for low carbon cement, it relatively take a longer time to cure, and also also sometimes may take a longer time for transport. So then by adding on technology, we are able to help to increase the upfront mechanical strength by having this layer of the tubing. It's like a semi kind of reinforcement. So actually we've been actually helping the low carbon cement type of mixture to really boost up the upfront performance. So this is a potential it could help. And also regarding different types of mixture, we could also select the type of heating agent that won't really have too much dependency on the material, the I think there's like
The
alternative.
chemistry of the concrete. Yeah.
Exactly, but mainly like we would like to open the door because we don't have limitations on different types of new mixtures. We're welcoming for any new type of solution providers that we could work together on the solution to help, like how we could enable each other better.
Okay. Okay. No, that's good. So I've got there's a question here about if that as I think we're assuming that the cracking will trigger the vascular system to work. Is that right? It's not a separate process. Okay. So if that's the case, how are you able to assure that your system itself can cope with the loading of the concrete and that there isn't any premature cracking of your system? What steps is that part of the process that you'll be testing as well under different loading?
Yeah,
Okay.
exactly. That's perfect question. So even before we move to commercialization, the first question we're addressing is, will the structural weakening the concrete? The answer is not to actually even help to increase the mechanical strength, which is previously out of our expectation, but is really good sign. That's why so we did normally the testing with the benchmark concrete and together with the benchmark the concrete with vascular system, and we do the classic testing. Currently we're working with AMRC at Sheffield, the standard testing body from a third party. So we're not handling the data ourselves. We're having the third party data to secure all the testing. So we're also validating the same performance as we promised. So this is like how do I say, it's like a third party approval from the testing procedure at least.
Excellent. Okay. So it all sounds very exciting. And so this is the work that you've been doing so far has been very much focused on rail, but you did present that there's some other potential. I wonder about lots of the projects that I've seen on self-healing have often been related to marine environments because of that potential high exposure locations there. So is this appropriate for marine as well? Does that also depend on the type of healing system that would be used?
Yeah. I think that's a great question regarding marine or like water defense scenario, because that's also one of our targeting market about water defense and the marine. But another consideration that we're also validating is actually how much impact, especially marine, is becoming more like a complex regarding the different types of animals and creatures and how we're impacting the general like ecosystem there. So that's why for MimiCrete as an early stage startup, we don't want to go high risk at the beginning. We're trying to validate in a relatively lower risk. That's why we're working on controlled risk. But then for water defense or for wastewater scenario, which is the part we're actually having like a higher tolerance for different type of material that can be trialed. For instance, like a wastewater, and when like the heavy metal chemicals or will be corroding the structure, and then we're able to help to repair and to avoiding further corrosions happening at the same time. So the scenario will be even more intense than the marine type of deterioration. But regarding like a risk and mitigation perspectives, as a new technology, we're on the way of climbing the ladder. So from the lowest risk and to high risk, and even like highest one will be imagined for like the drinking water and the marine or biodiversity. So that's like a stage.
That's it's good. Like a lot of innovation, you start at one point and then you can help and evolve once proof of concept is there. So I think we're gonna start wrapping up the questions, but there's one there was a question here that intrigues me that there's a lot of this is about increasing the life and of the concrete to some extent, or the health is the way I like to look at it. So if the agent is being put in at the manufacturing stage, how are you able to measure the life of that healing agent? Does that also last 100 years? Or is that something that can be topped up? How does that work? Or is that how are you investigating that as part of your
Yeah, and that was a great question regarding manufacturing, because normally we're splitting the manufacturing for vascular itself, for the healing agent, and also for the precast process. So from our side, normally for the healing agent perspectives, we do evaluating on the shelf life, and also we do the testing regarding the rheology, the viscosity of the healing agent that over time. So then we have like a tracking record of the performance in the system. But also, as you said, like for 100 years, we're trying to mimic, but it's such a long time. We're trying to find some data to calibrate. So that's why we're doing like a two-track work. One is doing the in-lab acceleration. The other one is we're trying to validate on site. So then we do like the calibration point to make sure that all the data has been somehow aligned to have a more accurate estimation. But also regarding the shelf life, for instance, which is that's why we're having the vascular system, which allowing new technologies or even to refill more healing agent to the structure if further kind of more intense environment happening, like as we know, like climate change now. So maybe a more intense structure happening, intense deterioration happening in the next 10 or 20 years. So that's why we're able to have this kind of factor and able to add in more healing agent afterwards.
Excellent, excellent. We have got a question. I'm going to say the final question we've got here is saying is can it be used with existing structures? But I think I know that the answer is no.
I would clarify, because now some of the existing structure are using precast. So if we're able to replace one of the precast, that is doable. But everything we're working on is the new type of format.
New casting. Yeah,
Yes.
excellent. Fantastic. Well, listen, thank you very, very much for the presentation, for your questions, and also to everybody who's asked all those questions. I didn't manage to get through quite all of them. There were quite a lot who wanted to know specifically a bit more about the polymer and the agents that we'll be using, but perhaps that's something that people can follow up with you afterwards on that. So thank you very much. I'm going to then just finally share my last slide, which I think hopefully you can all see now. And to draw your attention to our final Fresh Concrete event this year. Now we are going to have a presentation from Greg Williams of Sublime Systems. He's going to be talking about electrifying cement production to avoid carbon emissions. And these will be the principles that they've been developing there as a new technique for manufacturing low carbon sublime cement, its potential use and benefits. And who knows whether maybe that concrete could be used at one point to test out your system, Liz.
Yeah, definitely. We'll have to have a conversation.
Yeah, it'd be interesting to see how with a lot of that innovation. So please do, if you're interested in that, there's more details on the Building Centre website and the Concrete Centre website to book for that. It's Thursday, the 25th of June at 1 o'clock again, and you'll be able to log in and book right now for that. And also, just in case you're not aware, there's also, of course, all the back catalogue of the recordings that we've had over the last 2 years. So this is year 3 of our events. This is some of the innovations that we've been featuring over previous years. So thank you very much again. Thank you very much, Liz, today for your presentation, and hopefully see you all again next month. Thank you.
Thank you.